All right, guys. So in this case, we are going to need to work on our statics. That is the introduction of our statics. Just going to focus on the beams. Then we are going to have another class working with the cantilever. So this is actually as a request from our members. So that is, I just need to thank you guys for joining the membership. This is actually good. And also, for those who are part of MedZone African Motives, let's keep on revising as we are preparing for these exams. It is important that you understand the basics of the topics that you're going to be working with. So under your statics, you have this part of the beams. This part of the beams, it is something that we are not having for the first time, guys, since N2. Since actually N1, we've been having these beams, working with the beams and so on. So it is just going to be a continuation from that part. It is just going to be a continuation as we understand working with the beams. We can have the concentrated loads, all right? We can actually work with the concentrated loads in that case. That is any load that is applied to a relatively small area where we are given of this nature, then we are going to have our concentrated load facing down, all right? That is having a negative in terms of both in terms of the view. As we can see, it is going down, so it will be carrying negative in your calculations. So the concentrated loads, these are your point loads, all right? The ones that you refer to as your point loads, all right? We can have the uniformly distributed loads, all right? It's another part that you are also going to be working with, of which, guys, we worked with this. It's just a recap. Uniformly distributed. So it's gonna be distributed there. All right. So these ones, we understand they are the loads which are continuous. All right. So these loads, they are continuous and spread over the longitudinal axis of a beam. So if we are given such, maybe we are given 50 kilonewton per meter, we are given 40 kilonewton per meter, whatever that you be given, it will be of this nature, spread over a certain area, all right, a certain part of the beam. So maybe we are given a certain part, but this will be a certain force. So since this is distributed, I'm just going to use D like this, which is the distributed force, which is taken as the force that is measured in kilonewton per meter. It can be Newton per meter, but it will be per meter, meaning to say for you to have a certain force, which is now a concentrated load from there, just like what we had. Remember, we can make this to have or to end up with a concentrated load of this nature, which is now taken over a distance in between these 2 points. So for you to have that, maybe we've got this whole distance, which is called X. We are going to multiply the distributed part that we have, which is the kilonewton per meter, times the distance that you are given in meters. So by multiplying this, we are having this part here, okay? Which is taken in between. It will be in between. Now it is acting as what? As a concentrated load when it is like this. So, guys, this is just your recap, guys. What can I say? It's just a recap. We're gonna quickly go to the major part of our N4. So this is what we had, guys. Remember this, the part of the moments when you're working with moments, the sum of the clockwise moments being equal to the sum of the anti-clockwise moments. All that part, guys, the sum of the upward forces being equal to the sum of the downward forces. all that part you're going to need it. Knowing your reactions, if you're given a beam, the reactions, which are the supports, all right? These ones are the supports. These are the reactions. Okay, all these part, guys, you need to understand. So maybe we've got this one at A and this one at B. We're gonna call it RA, gonna call it RB. You can even call it FA. You can call this one FB. Just as long you understand that those are your reactions, and it can be any letter depending with the way that we have mentioned your these letters here, A, B, C, D, and so on. So that is it, guys. So I want you to just have this basic view. And also, in your basic view of your calculations, as you are having a recap of your N2, your N3, because I want you to work with that part. Remember, you also worked with the shear force diagram. All right, you worked with the shear force diagram. So that part, I'm not going to talk much about it. The shear force diagram, we worked with it, whereby you have to calculate, determine the shear forces that you're going to have, draw, depending with what you are given in terms of the, let's say in terms of your presentation. The type of the presentation that you are given also affects your shear force diagram. All right. So that part, like I said, guys, I'm not going to talk much. Let me just bring this one. All right. No problem. Sorry for that. I just wanted you to see this part so that I do not waste much time. This is the question that you're going to look into. Let me just take this one out. All right, no problem. So I want you to see this part here because we're not gonna waste much time, guys. All right. So here we have got this basic part. If you are to consider the part of the shear force diagrams, all right, when you are working with a concentrated load like this, how your shear force diagram is going to look like, where you have got a distributed load like this, we are going to have this line here, a slanted line of that nature. We are not going to have going up or going this side. We are going to have our line slanted like this when it is what distributed. So this is it. When working with a simple supported what beams, we are going to have another part which is working with the cantilever beams, which is another part on its own. All right. So this part, guys, is clear. You heard this in your N3. The only part that is now extended to you is this part of the bending moment diagram. For a concentrated load, your bending moment diagram is going to be going like this, okay? Take note where we have got this nature of a rectangle here. We are having a slanted line going up. When you are in the down region, you're having a slanted line going down. That is for what? For the concentrated load. For the distributed, you'll be having a curve whenever you are having a force whereby you're going up in this nature, whereby you've got this nature, okay? But now it's distributed. Look on your shear force diagram, what you have. Wherever you've got this part on your shear force diagram, what are you going to have on your bending moment diagram? It is going to be a curve going up. When you're going down, it is going to be a curve going down. So this is what you're going to have on your presentation of the bending moment diagram. This is the adjustment now that you have in your N4. All this part, guys, it was just your N3. All these shear forces that you are having, now that you are having formulas that you can use to calculate the shear forces, there, this and that. But guys, your shear forces, the way that you had your shear forces, yes, you can obtain formulas. Let's just have this simple presentation of how we can calculate the shear forces, and we're just gonna quickly go through our questions, guys. So let's say we've got this one as point A. where we've got a reaction there. And there we have got a force, which we can just call W1, which is a weight. Just guys, a force, we know that. All right, then we have got another one. Then this is the point that we are going to use to take our bending moments and also to take our shearing forces. All right, the shear force, the one that we need there on the shear force diagram. So I just want you to have a basic view of how you're going to use it or your calculations on a simple beam of this nature. All right, so this is it. This is it, guys. We have got the distances from this point A to this point X. I just need us to focus with these distances that I'm going to mark here. So we have got this distance. Let's call it A. This distance between these 2 points, let's call it A1. The distance between these two, let's call it A2. Then also the distance between this one and this one here, let's call it A3. Then the distance between this one and this one. All right, let's just call it B, like this. Okay, from B. So let's say we've got a beam, and this is what we are given. And we want to determine the shearing forces, the shearing force and the bending moment at section XX, this one, at this section. How can we calculate? All right. So let's have these two guys in view, because like I said, remember when you're determining the shearing force or the shear force, if you're at this point, you consider, okay, you're starting at this point. Which forces do you have there? You take the forces, all the forces that you have at that, on the left side of that point. Meaning to say, we do not have anything. We are going to take it as a 0. If you are at this point, you are going to consider to say, what is it that you have on the left side, the force that you have? That is about the shearing force, guys. It's not that something that is much. So let's just have it here. A shearing force, or when you are considering a shear force. So it is the algebraic sum of all forces to the left or to the right side of the section. So I'm saying it is the algebraic sum. The algebraic sum. Take note, once we say algebraic sum, you have to add all the given conditions that we have there. What it's about what? It's about all the forces. Algebraic sum of all forces, of all the forces, meaning to say to the left or to the right. So we must be careful there, to the right of the section. We must be careful in this presentation that is given here, guys. All the forces, we are supposed to add them, but to the left, or they can be taken here, or it's another part. You can work them to the right of the section. So if you choose to work to the left side, you work with you add the forces that you have on the left side. So if you're on this section here, this part here, we are working with this part. We have to combine all the forces that we see on the left side. If you're referring to the right side, you must combine everything that you see on the right side. But when working with the right side, you must reverse the forces, meaning to say a force with a negative, you take it as a positive. One with a negative, you take it as a positive. So I'll advise you that when working with the shearing forces, work with the left side, because on the left side, you do not make any adjustment there. There is no adjustment that you are going to make. What am I trying to say? Let's say we want to calculate this from the left side. I'm meaning to say to the left side. To the left side, we are going to obtain, that is to the left of this. Remember, we are using this as our axis, to the left of XX like this. So we want to consider the shearing force. So let's call it QX. So the shearing force in this case, as we consider the sum, remember I explained before on the intro that the point loads, the ones that are going down, they carry what? A negative. Whereas the support, they carry what? A positive. We know this one, guys, from our N2. So meaning to say, we are going to combine. This is the point that, the axis that you are working with. Okay, let me indicate it this way. This is the axis that you're working with, this one. So we need what is on the left side. The forces that we have on the left as they are. Combine them. So what do we have on the left side? We've got RA. It's a positive. It's going up. So it will maintain it's positive, this one, because it's going up. We have got this one, W1, which is F1. We can call it F1. So it is going down. It's a negative. We've got also this force 2, which is also going down. It's a negative. So we're going to subtract it. So subtracting these two from RA gives us what? The shearing force, which is affected to that point that you are working with. So as we can see, if you are referring to this point, you must work with the left side. What is that on the left side? We take what is on the left side. If you are working with this side, with this point here, what is on the left side? You combine the forces which are on the left side, taking note of what? The signs. So this part, it will be best explained working with questions by the guys. The shear force, as you had get when you were drawing the shear force diagram in your N3, don't even mind, guys. These see, they just want you to say, okay, maybe you want to calculate the shearing force at a certain point. That's why we've got these formulas, so that it enables you to even calculate the shearing force here at any point. That is why we've got the formulas. But guys, as you had those calculations without a formula, that you're just subtracting values. When it is going up, you add. When going down, you subtract. That part as it is, guys, from your N3. It's not gonna change. Okay. So that is the idea there of so like I said, to the right side, you have to change the signs. So RA, it's a positive, but you take, this RB, it's a positive, but you take it as a negative. So it will be something like minus RB. W, this force is going down. It reverses, so it will be a positive when you take on the right side. That's how you play around with your questions. So I prefer that you just work from what? The left side when you're dealing with the shearing forces, like we want to calculate a certain value. Then we have got the bending moment, which is the major part of our N4. The bending moment. So the bending moment, when we talk of a moment, bending moment is simply force times distance. Force times distance. So there is the distance. If we refer in terms of a formula, just like what we had there with our shearing force, the bending moment also can be referred, but it is the algebraic sum of the moments about the section. Force times distance about a section. If you're talking about this section, we consider the algebraic sum of those moments, but they must be from a certain side, just like, is it to the left or is it to the right? So that is what we have on the bending moment. So this one is the algebraic sum of the moments, okay, about the section. About the section. So it can be about the section of all of the forces, to the left, that is to the left or right of section. So this is what you actually need. We can work with the left side or work with the right side of the section. So what is important is that you have to combine them, but they can be to the left or they can be to the right. That is the most important part. You don't combine everything that you see on your diagram, guys. Because if you combine everything about that section to say what is taken from the left, what is taken from the right, you combine everything, you get a zero. So you only work with one side. If you are working with the left side, calculate from the left side. So about this section, if we are calculating the bending moment about this section x, this one. To the left, if we are referring to the left, all right, let's start with the one from the left. To the left of what? X, like that. So we want to calculate the bending moment of this, about this section, but considering from the left side. So on the bending moments, guys, it is going to be force times distance, like I mentioned before. It's simply force times distance. So you work with the force and the distance to that point, guys, to that section, I mean. Remembering also the signs. So meaning to say RA, remember, it's a support, it's a positive, this one. So it will be RA times the distance back to this section. The distance that we have there is what? Is this one, A, the whole of this one, the distance between. So it's a product. So we are going to have the force is RA, there it can be FA, depending with what you have, whatever that you have there, guys. So that's RA times what? Times A. Force times distance. It's a positive, this one. It's going up. From W1, this force one, this one, which is going back to X, like this one. This is the distance in between. What is the distance? The distance is what? A1. The distance in between. Remember, we need force times what? Distance. But it's going down. It carries a negative. So we're going to subtract because it carries, it's a point load. It carries a negative. So that's force times distance. Force times what? Distance. The distance in between is what? It's A1. The same part here, this force, what is the distance in between? The distance in between this section is what? It's A2. So it's going to be minus because it's going down. So that's force times what? Times distance times A2, this distance. That's how you simply take your bending moment. You have got the bending moments, the bending moment about this section here. If we were to take from what? From the left side. If you were to consider to the right, all right, to the right of what? XX, like that. You are going to have the bending moments this way. Remember, force times distance, considering the sign going up, positive, going down, it's negative. So let's consider force times distance. This time, we are considering to the what? To the right, this side. What do we have on the right side? The force there at reaction B times distance, which is the distance. The distance there is what? B, the distance in between this one. So it's positive, remember? So that's times what? Times B. On the bending moment, it is not affected, like I said, on the shearing force, to say when you consider the right side, you reverse the signs that no, no, no. For the bending moments, you maintain that it is not affected. What is going up, it's positive. What is going down is negative. So we have a force here, and its distance between this section, which is what? Which is A3. So that's a minus because it's going down. All right. So that's force times what? Times distance. Our distance, which is between the section. So this is just like a mathematical presentation. We are going to refer much of the calculations. Then in those calculations, we are going to talk about important things, guys, such as calculations of the maximum bending moments. This is so, guys, there's a lot. It's not a lot, but there is just a few things to recall and few things to add, which makes it a lot. So that is it, guys. After that, the presentation, this is what you're going to have on your bending moments, how you present them from these two types of loads, the concentrated or the uniformly distributed, from what? A simple supported beam. This is of a cantilever. This one, you're going to talk about it, guys, separately because it's going to be a lot. All right. So anyways, there's a question that we are going to consider with the information that we just had. We can try to attempt this question, guys, to try to figure out how to apply the information, the formulas, because it's not always that the formula is going to be applied direct. The formula is just a mathematical presentation, guys, which can be manipulated to the way that you want it to look like. All right. So in this question, we are given that the 8-meter beam in Fig 4.30 here is a uniformly distributed. So here, guys, there's a uniformly distributed. No problem. We're going to talk about that. 30 kilonewton per meter for the first, from the left end to 4 meters and 2 concentrated. All right. 5 meters, this and that. Left. Okay. No problem. So this is it, guys. There's a uniformly distributed load here. Then we have got these concentrated loads, which are the point loads. So remember, we are told that the wall of this beam that we are having, in fact, we are saying, let's put it this way, guys, so that we be clear. The beam is supported at both ends, at A and at E. So here at A, it's a support that you have there. There's a support here. All right. Then at E, support there. So you can just call it FA. You can, whatever that you want, guys. You can just leave it like that. So the 8-meter beam, the 8-meter beam, that is this one, the 8-meter beam. All right. Then it has a uniformly distributed load of 30 kilonewton per meter from the left here, from the left side, from the left end, all right, to 4 meters, all right, from the left end to, well, that is like they just want to say 4 meters from the left end. So that is what we have there, meaning to say here at point B, where the uniformly distributed is ending here. The distance that we are given here is what? 4 meters, meaning to say the remaining is 4 meters. All right, no problem. So of this remaining 4 meters, what is that we have? And 2 concentrated loads at 5 meters, 7 meters from the left end, respectively, from the left side. The first one is what? 5 meters from the left going this side. 5 meters, 5 meters like this. This is the first one. Let's see this one. It is what? 5 meters. Meaning to say, in between these 2 points, how many meters do we have? 5 minus 4. That's 1 meter there. The other one is what? 7 meters. All right. The other one is 7 meters. Sorry for that. Let me just remove this one. All right. The other one is 7 meters, meaning to say, as we are moving from this point, guys, right? This one. Okay, like this. As we are moving from this one to this one, the other one, because the other one is this one. This is the other concentrated load. 7 meters. This is what they are saying. From the left side. But remember, I told that the wall of this beam is 8 meters. So what does it mean? It means the remaining part here is going to be what? 1 meter, because this is 7, but the wall of the beam is 8 meters. So 8 minus 7 is going to be 1 meter. So we've got 1 meter, which is remaining here. That is it. Okay. So this is it, guys. Remember, there we have got a distributed, which is going to affect this distributed load that we are having is going to affect for the first 4 meters. So for the distributed load, guys, there is actually a lot of things that you need to consider there. Okay. If you are going to work with calculations for the reactions of these supports A and E, I said from your N3, you take this 30 kilonewton, it's just our distributed force per meter. You multiply 30 kilonewton per meter. Remember, this is per meter times the distance in between. It is covering how many meters? It is covering 4 meters. So once you multiply, guys, kilonewton per meter times the meter, you're going to remain with what? Kilonewton. So that was going to be 120 kilonewton, which you are presenting in between. So it will be like this as it will be a concentrated load now of 120 kilonewton divided between, remember, it was taken in within these 4 meters. So you take it in between, that is 4 divided by 2, which is going to be what? 2 meters. So it will be it will be separated, I mean, between the 2 meters here and also another 2 meters. The in between, it will be acting as a concentrated load. So this part is helpful when you are working with the calculations of the reactions of A and E. We're going to see it about that one. No problem. So it's not always where you're going to take it like and it's applied, because it depends with the situation. There can be 2 of them here placed differently. We're going to see questions of that nature. They can place 2 different distributed loads, uniformly distributed loads on the same section. Another one may be starting from this section, starting from this point where it is starting here to this point, being distributed. All right, no problem, guys. We shall see those in another part where at least we are doing question papers. So these were the questions that we are given. Of these, using this information that we are given, calculate on 1.1 the reactions at A and E. All right, so we need the reactions at A and E 1.1. So the reactions, guys, I think this one is now direct from your N3. We said that the reactions. All right, let me see it. I have something. I just wanted, guys, something which is where we do not have a lot of working. All right, no problem. Here we have got space. No problem. Let me just work here, guys. We can even use this space. It's not a problem. So that's 1.1. So remember about your reactions. This is the part where I was talking about the issue of the clockwise moments, anti-clockwise moments. All right, so let's start about taking our moments about E. All right, so taking moments about E. All right, so using the point E, if we are to consider A going to E, All right, look the way that A is going to move to E. A is going to E. Which way is this? That is clockwise. So we are going to consider the sum of the clockwise moments being equal to the sum of the anti-clockwise moments. So that is the case. So the clockwise moments are the ones that are going this way, the way the clock moves, the clock like that. Anti-clockwise, the other way. That is anti-clockwise, the other way, all right, of your clock. So this is it. If you are to consider the clockwise, we have got A, which is going back to E because E is our reference part. What can I put here? Um, Let me just put this one here. E here is we are referring back to this point of E. All right, don't mind this. Don't mind this, guys. Like, we are just referring from this E. So meaning to say, if we are referring back from this E that we are having, every part that we are going to have must be taken back to the E. All right? So let's consider A to E. It is what? Clockwise. This A here, it is going to be going in the clockwise. Which other part that is going to be clockwise? That is the only part going in the clockwise. If we consider this going back to E, this is the direction. It is now anti-clockwise this way. That is what? Anti-clockwise. So you're going to see that D going back to E is anti-clockwise. C going back to E, anti-clockwise. This part that we have made a concentrated load going back to E, it's also anti-clockwise. So all these guys, the D that we have here, I say these ones, they are anti, also this one is anti-clockwise, all right? So that is it, guys. Let's add up and see what we are going to have. So remember, force times the distance to that point. That is the force here at A times the distance to E, the whole distance, which is 7 plus 1, which is what? 8 meters. So that's A times 8. So that is what we only have on the part of the clockwise moments. Anti-clockwise, all right, let's start with these ones closer to E. We're going to start with D. So D back to E here, force times distance, remember. So what are we going to have? It will be 40 times 1. So that's 40 times 1. Okay. We move on to this one, the 20 back to E. This one, 20 back to E. What is the distance in between? Remember here we've got 1 meter. So we need the distance here from here. All right, let me show you this way. From here, from this C back to this one. This is the distance that we want here, this one. So out of this distance, we can see that there is a 1 meter already. We want this one, the remaining part here, so that we can add. So where are we going to have this? All right. Remember, the wall of this part here, it was 5 meters here, this one. It was 5. And this one is what? 7. So meaning to say 7 minus 5 is going to be 2. So we have got 2 meters here, then 2 plus 1, which is 3. Or you can just calculate the whole of this distance at once. From where? From the 8 meters. Remember, this beam is 8 meters. So 8 minus 5, this one, this 5 here. 8 minus 5 gives us what? A 3. So it's 3 meters here. That is the idea. So we need, guys, that distance, remember, because we are going to need the force times the distance back to that point. So that is it. We are going to have plus 20 times what? 20 times 3. So that's 20 times 3. All right. We still have another part in the anti-clockwise. It's part of 120. So remember, it is now 120. We multiply 30 times what? 30 times 4. So it's 120. Back to what? To E. Back to the point E. We have to add the distance. All right. So remember here, guys, we are here. Back to E. So if you consider there is 2 meters plus 1, which is 3, plus these 3, which is 6. So the distance there is what? 6 meters. So that's 120 times what? 120 times 6. All right, just like that. So you have to combine all this part, all right? It's going to give us 8a. So 8a is equal to the sum of these guys. You multiply and add. That was going to give us 820. So dividing by 8 by 8, you now have an equation here that you need to solve for a. So a was going to give us 102.5 kilonewton. All right. Sorry, kilonewton, like that. So this is the part of our reaction. Managed to calculate this. All right. So this is our A, guys, 102.5. So I'm just gonna write it aside here. A is equivalent to 102.5 kilonewton. So using the same part, we are going to take moments about A and quickly have our value of E. All right, so that is it, guys. This time, let us take moments, taking moments about what? About A. So about A, this is where we have our A, guys. We are now having from this side, all right? This is where we are now having our reference. So meaning to say E, as it is going back to A, look at the direction, this one. Which way is this one? Anti-clockwise. So it is going in the anti-clockwise. A, as it was going to C, it was to E, it was going in the clockwise. But C, I mean this point E here is going to be another way, anti-clockwise. So meaning to say we are going to need the sum of the anti-clockwise moments to be equal to the sum of the clockwise moments. Which ones do we have in the anti-clockwise? Remember, we are referring back to this one, A. So E is going in the anti-clockwise, which is fine. Do we have any other one? No, this one is going to be this way clockwise. This will be clockwise. This will be clockwise. Remember, this is how the clock moves. So all these ones will be going in the clockwise. So that is it, guys. They are referred to A, remember? So they'll be going this way. Clockwise. This one will be this way. This one is going to be this way. They'll be going in the clockwise. It's only E which is in the anti-clockwise. All right, so let's take that, guys. That is E back to A. That is E times 8. The distance to A is what? Is 8. So this is part of our anti-clockwise is equal to the sum of the clockwise moments. All these other part, we say they are in the clockwise. So let's start with 120. 120 back to A. There's a distance there of what? 2 meters. Remember, it's in between 2 meters. So that's 120 times 2. This one is direct. 120 times 2. You move on to another one, the 20 back to A. So the distance there is gonna be what? 5. We already have the distance here between is what? Is 5. So that's 20 times 5 back to A. All right. That is here. All right. 20 times what? 20 times 5. That is 20 times 5. Then we consider the 40 back to A here. So the distance is already there. That is the 7 meters here to 40. There's a distance there here, 7 meters. So that's 40 times 7. All right. So already the distance we obtained it. So that's the advantage of analyzing your diagram first. You see, it will be just a matter of substitution into the formula because already you have all the values there. All right, so that is it. Calculating the left-hand side, 8 times E is going to be 8E is equal to, you combine everything on the right-hand side, it was going to be 620. So divide by 8, you're going to have the value of E, which is 77.5 kilonewton. So after that, guys, you can even prove, remember the sum of forces going up must be equal to the sum of forces going down. So that is the case. That is the case. All right, just like that. So this is our E. Just gonna remove this part, guys. We are done this part. So our E in this case, we got 77.5 kilonewton. So like I said, you can simply prove this, guys. Remember that when dealing with the forces, the sum of the upward forces must be equal to the sum of what? The downward forces. Meaning to say, if we add A and E together, if we add A and E together, we must have the sum of these three forces, the 120, the 20, and the 40. So I want you to add that and see you're going to have truly those two being equal. So that is the case of your reactions, guys. This is our N3. We are just we're just having a recap of N3. Now N4, we are starting now here. 1.2. Calculate the bending moments at B, C, and D. All right. So actually, remember what I referred to. Okay. Bending moments here. This is of the bending moments. You'll be multiplying first time, all the adding everything, all the algebraic sum of the moments. So if you are at this point A, on the left side, what do you have on the left side? There's nothing. So it means that's a 0 there. If you are at B here, at this point here, what do you have on the right side? There's nothing. It means there's what? There's 0. That is why on our question here, if we are to consider our question, they did not focus about A and what? A and this point E. At A and at E, the bending moments there will be what? Will be 0. So those ones, you just need to know them, all right? So at A, the bending moment at A is equal to what? To 0. So remember, moment, that's kilonewton meter, force times distance. So it will be kilonewton meter. And also the bending moment at C, not C, but E. Where am I getting this C today? This is E here at the end point there. That's 0 kilonewton meter. All right, so let's focus with B, C, and D. How do we calculate the bending moments of these? As I mentioned from the formula, we need the sum of the moments that we have. Is it from the left side? Is it from the right side of that section? All right, so let's start with B. I just hope my diagram is going to be clear, guys. Or if I minimize, I hope you'll see it, guys. I hope you see it, no problem. So this is it. We are going to have 1.2. So the bending moment at what? At B can be calculated. Let's say we are referring to the left, right? To the left of what? Of B. Where are we having B? This is from our diagram here. This is where we have B here. This is where we have B. So considering this part, guys, we are saying to the left of it, to the left of this part B here, to the left side, add, combine all the moments there, force times distance, force times distance, that you see on the left. Knowing that everything that is going up is positive, anything that goes down, negative. That is the bending moments, guys. You just have to combine everything, all the moments, force times distance. So from the left side, what do we have? We have got A times the distance back to the section, back to the B there. So what is the distance? A back to B, it's what? It's 4 meters. So that's A. Remember, we calculated A. Here's our value for A. So that was going to be 102,5. That's 102 comma 5 times the distance, which is what? 4 meters. So this one, it's positive. It's going up. Do we still have any other force on the left side of B? Yes, there is a 120 there. So take note, it's distributed and ending at B, this one. So we take the whole of this distributed. Guys, be careful, because sometimes this distributed can be like this. Let's say, right, I just wanted you to see something here. Let's say this distributed load was like this, going here like this. It was covering up to that side. You were going to take the distributed that starts and ends at B only. You're going to consider this part. Let's say it was there was another section of the distributed here. You are going to consider only this section, meaning to say you work with the distance. If it is like that, it will be best that you use this concept of using the force per meter that you are given. So you calculate this way, 30 times the distance that you are given, which is what? Which is 4 times the distance back to that point here, as it is being distributed, which is what? Which is 2 meters. But in this case, because our distributed load, which is our uniformly distributed load, this one, it is taken in within, from A to B, in within that section that we want to calculate. So there is no need for us to make these adjustments. Guys, please bear me well. These adjustments will be needed in our questions. So you must be very careful on the bending moments there. So this one, remember, is going down. It's a negative, so it's going to be minus 120 times the distance back to B, which is 2. Like I said, here there is no further adjustments. It's just direct, this one. So multiplying these two, combining together, you are going to obtain 170, that's kilonewton meter. You were taking this to the left. You could have considered taking to the what? To the right of it, to the right side. If you are considering to the right side, what were you going to have? The bending moment at point B. Considering this is the right side, considering the right side, force times distance, force times distance, what you see on the right side. So let's start with E, which is positive, because E is going up. So it's E times the distance back to B. What is the distance? So remember, E is 77,5 is positive times the distance back to what? Back to B. What is the distance? That's 1, 3, which is 4, plus this one, which is 4. That is 4 plus 1, which is 5. So that's 5 there. So that's, guys, oh no, the 3 is covering all this part here. So it's simply 3 plus 1. So that's 3 plus 1 there, which is 4. All right. So the distance there is what is 4. Remember, the 3 is this whole part here. This is our 3. So that's 3 plus 1, which is 4. So the distance there is 4. All right. This one, the 40 kilonewton is going down. That's a negative. So force times distance back to B. So that's a negative, that one. Negative 40 times what? The distance back to B. Remember, we said the whole of this part is 3. But this one is 1. So 3 minus 1 is going to be what? It's going to be 2 here. So 2 plus 1, which is 3. 2 plus 1, this one. It's going to be what? It's going to be 3. 2 plus this one. So that's the distance there is 3. So that's 40 times 3. It's going to be a negative, that one. Then 20 back to B. There's another force there, force times distance. So it's going to be minus 20 times what? The distance back to B, that's 1 meter. So that's 20 times 1. You combine all this part. It was still going to give us the same answer of what? 170 kilonewton meter. So that's in your hands. It's in your hands to calculate the bending moments, guys. It's in your hands. How are you going to have this? All right. So let's consider at C. So this time, C is our reference. We are working with C this time. All right. So let's put this one at C. Okay. This is the part of our C. So they want us to calculate the bending moments considering the point C. So if we are to take to the left, okay, if we are to consider to the left, what is it that we have on the left? Force times distance, starting with the positive, back to what? Back to C. So we've got A back to C, which is the distance from A to C is what? 5 meters. So remember, we calculated A. So this one is direct, guys. So it's going to be A, which is positive 102.5 times the distance. A to what? To C. This time to C, our reference is C. So that's 5 meters. All right. Do we have any other force on the left side? The only force that we have is this 120 distributed and ending here. So it's 120 times what? So it's going to be minus because it's going down. So it's negative 120 times what? What is the distance? The 120 back to C, to C, to C. Reference is C. So how many meters? Remember here it's 2 meters. Here it's 1 meter. So if we add the 1 meter here, 2 plus 1 is going to be what? 3 meters, just like that. So combining these two, it was going to give us 152.5 kilonewton meter. Just like that. So you can even, guys, work with the right side. It's in your hands. The bending moment at C, you can even work with from the right side. Let's try to figure out what's going to happen if you work from the right side. You must have the same answer. You must have the same answer. To the what? To the right. So to the right, we are referring this side. Force times distance back to C. Force times distance. Force times distance. So there's a force here, which is positive, times distance back to C. So what is our distance from E to C? That is this one. Remember, it's what? 3 meters. So that's 77.5 times 3. Remember, this is positive. Is there another force that we have on the right side? Yes, there's a force here on the right side, 40 with a negative going down. So that's minus 40 times the distance back to C, back to C, back to C there. What is the distance in between these 2 points? Remember, it's what? 2 meters. 3 minus 1, we said it's going to be what? 2 meters. Just like that. So it was going to be 152.5 kilonewton meter again. So that is the case. We have the bending moment at what? At C. So I want you to use this in your calculations, guys. Try to figure out as much questions as you can. Do as many question papers. Science it's a lot. Science is always a lot, guys, as we understand. So try to figure out how questions are given. Then we move on, the bending moment at D. So at D, this time our reference is going to be here, D. Remember, this is where we have D here. We are working with this D. Force times distance back to D. So let's work from the left side of D. So this is our D. Bending moments at D. So I'm just going to consider to the left so that we see in terms of our calculations, but the easiest, the path was in terms of exam. Here we're just doing an introduction, but in terms of exam, the easiest part for you was going to be what? The right side. There's only one force there on the right side. And for you to work with the left side where there are a lot of forces there, but still, it's a introduction, guys. So positive, remember A is positive. A back to what? To D. How many meters do we have to the point D? How many meters from A? That is the 7 meters. So that's A 102.5 times 7 meters back to what? Back to D. There is that 120, the one that we obtained there, guys, the 120 Newton there. So it's carrying a negative. So that's minus 120 times the distance back to D, distance to D. How many meters? Remember here is 2 plus 1, which is 3, plus these 2 meters. The 2 meters is covering here. So it's 3 plus 2, which is what? Which is 5. So it's going to be 5 meters. Okay. Is there another force on the left side? Yes, there's 20 Newton, this one, 20 kilonewton. So you're going to subtract that one. 20 times what? 20 times the distance. 20 back to what? Back to D. What is the distance? The distance is this one, the 2 meters. Remember, we got 2 meters there. So it's 20 times 2. So that was it. You combine everything, that was going to give us 77.5 kilonewton meter. You've got your bending moment at what? At point D. Just like that. Just like that. So the easiest path, like I said, it was supposed to be working from the right side, guys. Working with the bending moments at this point in exam. There's no need for you to stress yourself going to the from the left side. You can just work from what? The right. So from the right side, what are we going to have? Do we have any force or any force on the right side? Yes, it's there. There is a force there of 77 comma 5, which is positive. It's going up. It's positive times the distance in between that force and the section that we are talking about. So it's 77 times what? Times 1. Remember, it's going up. So that was going to be 77.5. Just like that. Same answers. Same answers. That is the only force that we have, guys. Don't force yourself to add a lot of forces that are not there. That is, we end up now having mistakes in exam. You try to figure out this force which is not there. Guys, work with what you are given. Just like that. So that was it, guys. This part of the bending moments. Remember, I said at A and E, those are the starting ending points. Our bending moments, there will be what? 0. Then we move on to this part 1.3. It was draw, neat shear force, and bending moment diagrams and indicate all the major point values. Indicate all the major point values. Indicate all. All right. So I want you to see this. The shear force diagram, guys, it's basic. This is your N3. So it's just going to be a continuation. We're not going to waste much time. We're just going to use this one. But I just want us to take 1 or 2 from what we had. Remember, I said we've got the reaction at A, which we calculated. It was 102.5. It was 102.5 kilonewton. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Why are they 11? Like, am I counting? 1, 2, 3, 4, 5, 6. All right. 1, 2, 3, 4, 5. Does not correspond. No problem. So I just wanted to see, like, what does it? Okay, but no problem. I'm just gonna put it this way, guys. No problem. But that is we just have one distributed part there, so it is not going to give us much stress. 30 times the 4. Remember, the wall of this part, it was 4 meters. It gave us 120 kilonewtons. All right, then we also calculated this one at E. Remember, E gave us 77.5. This was 77.5 kilonewton like this, okay? So this is what you actually had from your view or from this presentation. Okay, so we need the shear force diagram. Let's start with this one first. The shear force diagram, as I uh, actually indicated, guys, in our N3, we do understand that when we have a distributed load like this, we are going to have a slanted line like this. Okay? Whenever we've got a distributed load. When it is going up, it is going up. When a force is going up, we are going to go up. When a force is going down, you go down. But for a distributed, guys, it will be like this for a shear force diagram. I hope you still have that part of your N3. So meaning to say the first point, it was going to be starting initially, you'll be at 0. Initially, you start at 0. Then what happened? Definite, guys, you'll be having, so there'll be some other guys asking, why don't you use a scale when you are drawing these, this and that? So guys, here to have a scale is going to be something else. You are the one who's supposed to have a scale when you are drawing. If you want to have that one up to a scale, but according to the values that you'll be given, mostly indicate the values that you'll be given. Yes, you can roughly say this can be at a certain value. Roughly, you can see it can be at a certain value. Not to say if you want to properly subdivide, guys, this is you see, guys, the part that I'm using. It's a blank page. This one I can't like properly measure to say here exactly, but I just want you to see how you're going to have it and the important points. All right. So you start at 0. What happens at A? There is a support. Remember, support's positive. You're going up. So you started at 0 and there's a support. You're going to add the support. That will be 102, comma what? Comma 5. So if you add this, guys, it will be what, just 102. So you go up straight, guys. It's a support. So as you draw a straight line straight to 102.5 according to the scale that you have used to say, okay, according to my units, this one, it represents this. So let's say your 102.5 is here. You mark your point there. That is where you have what? 102.5 kilonewton. This is our point along the straight line going up. Then there is a distributed load, this one, from A to B. From A to point B. There is no other point load. Remember, this 120 is the one that we actually calculated from 30 times what? The 4 meters. This one, it was covering what? It was covering the 4 meters. So under exam, let's say there's another, because they can have a distributed, and then there'll be another point load in within that distributed. You calculate for a certain interval. How do you calculate for a certain interval? You just multiply, guys. First time, like here we are at what? 102. So it will be 102.5. You subtract like this. So you multiply 30 times the distance covered for that section that you'll be calculating. In this case, it is lucky enough that it is covering the 4 meters, the one that we have. So that 120 that we had is still the 120, 30 times 4. After that, what are we going to do from there? Do we have any other part that is left, any other force? We do not. It's just that distributed, because it can be a section where there is another point load. But in this case, it's just that distributed. So that is the lucky enough of our question. There is nothing that we have. It's still that same 120 that we had. No adjustment. So that was the lucky part of our question. So it was going to be negative 17.5 kilonewton. Remember, a distributed load, I said, I mean, if you are representing this, it's going to be what? A slanted line like this on a what? On a shear force diagram. So it was going to be a slanted line to negative 17. Let's just say negative 17, guys, according to your scale, it's somewhere there, guys. Remember, I said, yeah, I'm not going to have what? I'm not going to have a proper scale. So let's say this is where we have our negative 17,5 kilonewton. Let's say we have at that point. You were simply going to join, all right, from this point to this point like this. Oh, sorry, guys. Yeah, we started here. We are at this point here. Yeah. Remember where we are here. Here to this. Sorry for that. This is where we are at 102 here. So you join to that. As you can see, automatically, you're forming what? A slanted line. That is what happened in between these points. Then from that point, B to C, there's a distance there to be covered between B and C. There's nothing, just empty. So you just move straight from B to C. You just move straight. There's no distance there. That is I mean, there is no force that we have that we are going to subtract or that we are going to add. So you simply move straight in a horizontal. So this is direct at C. So at C, what is happening? There is a point load. Remember, I said point loads, they take a negative, guys. This is your N3. Guys, explaining this will be like, guys, you're now confusing us because you had this in your N3. So minus 17.5 minus 20. Let's quickly have this. It was going to be minus 37.5. Minus 37.5 kilonewtons. So remember, it's a point load. It goes down straight as it is to minus 37.5. So let's just assume our negative 37.5 was here according to your scale. You're going to join from that point straight going down to negative 37.5 kilonewton. All right, so that is the case. Then from C to D, there's nothing in between. So it will be just a straight line maintaining the same value that you obtained of negative 17, negative 37.5 here. It is still the same value that you have at what? At point D. Then at D, there is what? A point load there. A point load carries a negative. So meaning to say at negative 37.5, we are going to subtract what? We are going to subtract a 40. So it will be minus 77.5. So it was going to be minus 77.5 kilonewton. Remember, it's a point load. It goes down straight. From here, it goes down straight. So let's say our negative 77.5 was somewhere here. It was going to go down straight to that value of negative 77.5 kilonewton. Then from there, from D to E, what do we have? Nothing, is just open space. So from D to E, we're just going to maintain an open space like that. Okay, like this, open, like that. Like this is what we have from D to E. Then from that E, what do we have? At E, there is a support. Remember, a support, it carries a positive. We are going up, but up to where? We must add that 77.5 here. So adding this, it was going to give us a 0. So as you go up, you are going up to where? Up to 0. So that is the case, guys, of your question, guys. Just forgive me this. I can't be accurate enough. But this is the case. Here it's going straight to that point, straight like it's corresponding. Point C corresponding. The point B there correspond like that. So this is exactly what you're going to have at the end in terms of your presentation. In terms of your presentation, you were going to have something of this nature. So guys, just do more questions. I'm going to also bring up more questions so that we try to figure out how are we going to have our diagrams, this and that. So from there, they need a bending moment diagram. So you're just gonna, at least, let's just try to have a continuation from this one that we have. So let's see, what are we going to have on the bending moment diagram. So on the bending moment, guys, okay, let's extend this one. Let's just try extend this. And according to our diagram, we're just gonna be this one. It's if you are to consider, it's let's go back here. We are dealing with what condition where there is a concentrated and also a distributed load, like something like that. So you're going to notice that your bending moment diagram is going to be on top. All right. It is the part of a cantilever where you're going to notice your bending moment diagram drawn below the x-axis, this one. But ours, for a uniformly distributed, concentrated, it is going to be drawn on top. But it follows this, guys. As you are going up in this way, as we're going to have this way of a slanted line. For a distributed, you have a curve like that. But you have a point now when you are having your bending moments, like when you are to calculate, when you are dealing with the bending moments, you have a section, let's say there is a distributed like that. Then there is a point, whatever load, a point load. It is going down, it is going down until it gets to zero. You reach a point where you refer, or where you have the maximum bending moment. At that point, you are saying this is the maximum value, which is also a point of inflection. Remember, on points of inflections, we have got the 0 points on point of inflection and the maximum point. Those are the points of inflection. The 0 points and the maximum. So at the maximum bending moment, it will be a condition, guys, that you have to consider according to the question that you are given. This one, guys, you must be careful. You must consider according to the question, but it occurs at in condition, on a condition of our question. It is going to occur from here, from our shear force diagram. You see where we have got this distributed when it crosses our x-axis here, where it crosses, where it cuts the x-axis here. That is where the maximum bending moment occurs. It occurs at this point. All right, at this point. So for you to have that maximum bending moment, you remember, guys, we are talking about bending moment where we are going to be referring to the force times distance to that section. So if you are to consider here, we are going to need the distance to this point. Because our diagram here that we are having, it is not accurately enough that we can measure. Yes, we can. If this is to scale, you have drawn this, guys, to scale. You have drawn it to scale, You measure and you also consider, all right? To say according to your scale, maybe you use 1 centimeter to represent 2 meters. You measure whatever that you have according to your scale. But in this case, we do not have. So we are forced to calculate this distance from this point to this point here. Let's call it y like this. So you calculate that distance. Remember, we are saying our maximum bending moments, or it occurs at this point. So we need the value. So you're going to calculate that distance y. From which concept? We can simply calculate it from the shearing forces, or from the forces concept. Because remember, from our forces, guys, we're saying we can calculate the forces if we are referring at this point. We do not know exactly, but it is somewhere there like here. We do not know exactly. But these forces will add up to 0 at this point where it cuts the x-axis. Your forces will add up to 0. So the sum of the shearing forces will be equal to 0 at what? At x at this point. Let's call it x at x, which is where the maximum bending moment what occurs, where the maximum bending moment occurs, sum of forces there will be equal to 0. So we can take advantage of those because already there we have got a force which is given directly from A, so it's positive. So we're gonna take 102,5. Then remember there's a distributed, but this distributed now it's no longer 30 times 4. It's no longer covering 4 meters. It is covering this distance of y. From here, we do not know where exactly where we are going to have the distance, but it's covering a distance of y there. So the force that we are going to be having, remember this, it will end up like this, guys, taking a negative. So it will be negative 30 times y, where y is what? The distance that we have from that point to what? To A. This distance, the one that we need to calculate that one. So remember, at that point here, where we have got the maximum bending moment, the force there will be equal to 0. So combining the sum, getting a 0, we can solve for what? We can solve for y. It's now an equation, guys. It's now an equation. This one, 102,5 is equal to, take this one to the other side, it will be positive. So that will be 102,5 is equal to 30y as a positive. So divide by 30. Divide by 30 like this. So y is equal to, so it's going to be something like 3,417, something like that in meters. So this is the value of y, the distance where we are going to have what? The maximum bending moment, the distance that is being covered. The distance that is being covered there. So once you have this distance, how do you calculate your maximum bending moment? Guys, don't worry. We're going to draw that bending moment diagram. Do not worry. I need us to finish about this one first. So in our condition, when you have got a distributed load like this one, you can use this formula. As long there is no other force in between, you can use this formula. But if there is any other force, you have to make adjustments to subtract that force. I'm going to talk about that maybe when answering question papers. But you can use this formula, guys, that the maximum bending moment from our condition where we've got a distributed load, where we've got this type of a section, you are going to take this force here. Let's just say this is our A. So this is the force at A. All right. So we are going to take the force at A, which is A is just like our starting point. So this is the force at the starting point times the distance y, this one. Remember, force, moment, force times distance. Then we are going to subtract for the distributed load. Remember, there's a distributed load. So it works when you have this distributed load. So it's going to be FD for the distributed load times y squared over 2, like this. So this is the formula that we can simply use to calculate the maximum bending moment as long as you've got this distance. So if in terms of you have something that is proper to scale, which is properly to scale, you measure, you take that value, guys, you measure. Here it is because of not having a scale. You're going to have something like 3,4 from your calculations. Then use the formula, just like it won't be too much from that because already here you can see it, guys. It's just taking a ruler you measure from. Then you put back to the scale to say, if you were saying 1 centimeter represents 2 meters, then what about what you measured? How what is going to be the measurement in terms of what? In terms of the meters. just like that. So let's substitute, guys. The force that is at point A, our first point. That's our first point where this where this condition happens, guys. Wherever you have this condition, so there can be something behind here. You subtract it once it's there. So you're going to make adjustment. But once you have this condition here that I'm presenting, this will be your FA. This will be part of what? The distributed. Remember, this will be your Y, just like that. So you can it's only for this part, like it's best for this part. But we can use for any, guys. I'm gonna talk about this only issue of time. Issue of time, guys. Issue of time. We just hope that time will be on our side. You see, time, guys. Time is money also. But you guys, okay, no problem. Let me not talk about you guys. Let me finish up. All right, so FD, our distributed, that is 30. Remember here, so that's 30 kilonewton there. That's 30, 30, 30, 30. All right, guys. The network is trying to fight my time now. So that's 30 times y squared, the distance, 3.417 squared over 2. Like this, you're going to have your maximum bending moment of 175.1 kilonewton meter. Just direct. It's a direct thing, guys. It's only that we had to calculate this distance otherwise. But even if you had to calculate, guys, it's just like small thing. Then after that, apply your formula. You are done. So knowing this, guys, we are supposed to know that when you calculated here, these bending moments, remember, here, I'm just going to reduce here so that we see what we had. We calculated the bending moments, remember, from A up to E. All these bending moments. Know that there is a maximum bending moment as you are representing your diagram. Know that is there of 175.1 kilonewton meter. So we need it. This one, we need it. So 175, it's in between what? Remember, at B, it's 170. At C, take note at C, it is reducing. So it means this 175.5, the maximum bending moment, it's in between. It's in between B and what? B and C. It's in between B and C. In between here. This is our A. This is our B and C here. In between, when we are to present. Okay, let's present, guys. Let me remove some of these things. So that's the case. Just like that. Simple. It's very simple, guys. Just do a lot of questions. You're done. Where there are questions, the comment section is there. Let's communicate. Also, the members, if you're a member, I want you to comment on this video so that we know the members, the ones who made this possible for this video to be available on this platform. Can you also comment on the comment section? Let me know about areas that are to be done. If anything is clear, let's communicate. If you're a member, even if you're not a member, guys, you're part of Med Zone African Motives. Let's communicate. All right. So I was saying we need that between those points. Okay, so let's start at 0. So let's start. Let's just gonna have this. Just a simple part. Okay, let me choose like. So the bending moment is for us here because it's not a cantilever, this one. So definitely it will be above. It will be above. So that's why I'm focused about on top, being on top. So that is it, guys. So I erased something. That is okay. I did erase something here. So here I've got bending moment diagram. So this is it. On your bending moments, starting the point A there, which is at 0. So remember, we have got the first one, which is at what? Which is at 0A. It's at 0 there. Then we move on to B, which is 170. So B, it's 170. All right, guys. I was saying this is 170. This is 175. So then you say this one must start. Okay. Yeah. Someone's mind is tired, guys. This is 1 hour. All right. No problem. Let me finish up so that I can rest, guys. So this is it. This is the maximum, this one. It is actually above this B. I thought, hope someone saw this. It's above B. B, it's 170. So meaning to say, as we move from 0 there, remember it's distributed. So distributed, we are going to have what? A curve like this. Here, we're going to have a curve. It's distributed, uniformly distributed. So we'll go with a curve like this. But that curve, it will reach a maximum value. It will reach a maximum value before it reaches B. So it will be like a curve, then it goes back, something like that. Guys, I hope you are with me. I hope you are with me. That is what is happening there. So it's gonna be like this. Okay, it is going up. It's a curve to that value that you'll be having. So at B, it goes down. It is now going down. It is now going down. It is now going down. Something like that. At B, something like this. So here is supposed to be something like it's supposed to reach a certain peak value there, yeah, around this one. To be at the peak value there. Which is something like that, which is here, which is at that point, it is corresponding to the maximum there. This is the maximum bending moment. So according to your scale, this and that you'll be having, that one is going to be your 175, 1 kilonewton meter, your maximum bending moment. Then at B, it is reduced a little bit because at B, we are now at what? We are now at 170 kilonewton. Remember, at B. At B, it's now 170. It is reduced. It has reduced. From 175, we are now at 170. At C, all right, take note, from A to B, we have covered the distributed load. We have covered that distributed load. This is the one, the curve party. We have covered the distributed load. So we now move from B. From B, we no longer have distributed loads, guys. So as long we are presenting something where we do not have the distributed load, where they are concentrated loads, when going up, we are going to be presenting like this. When going down, we are going to be presenting like this for bending moments. So it will be slanted lines this time. We are using what? Slanted lines. So from 170, which is at B, to C, all right? To C, it's what? 152,5. So C is somewhere, 152,5, maybe somewhere there. You are using the slanted line now. I mean, this one, the slanted line to join. This is where you have your C. Maybe that is where you have your point there, 152,5 kilonewton meter. You move on to the D. What do we have at D? You calculated this at D, it's 77,5. So at D, somewhere there, the slanted line again, you are joining with what? The slanted line. You are now that point. So it will be just those slanted line and so on, guys. So this is now at 77,5 kilonewton meter. Then the last one will be E, which is our end point, which is at 0, the end point there. It will be what? At 0. So E, which is at the end point, maybe somewhere there. So we're going to join from that point to this point. That will be what? At 0. So it's not like it will be a straight line like this, like straight. No. It will be just like, those guys, something like you're here. Then another one is just like going down, another one, something like that. So it's not going to be like just straight. No. So that's it, guys. These are your values. So we are back to 0 there. We started from what? From 0. So we have a closed figure, just like we have a closed figure on the shear force diagram. So this is your bending moment diagram. This is your shear force diagram. So that is your N4, guys. You need this. So there they now asking you on 1.4, show how you have determined the magnitude of maximum bending moment and its position. So guys, I talked about, this is the one that we're talking about. I think I erased it, but already I talked about it, how you obtained this maximum bending moment, this one, and its position there. The position why it was what? It was 3 comma, yeah, that position there. Why there we calculated it was 3 comma 417 meters. Remember, that's the position. So guys, we talked about this one. So those are the formulas and the presentations that you were going to simply need from what you had. So it will be corresponding, guys. There will be corresponding. B to be corresponding like that. C will be corresponding. D will be corresponding. A will be corresponding to the end. So that is how we are supposed to have these diagrams. Just try to work out as many questions as you can, as many as you can now. Try to figure out how questions are being given, calculations of the bending moments, this and that. So that's it, guys. From Meson African Motives, till we meet again.